Hi everybody, I'm Patrick Massot from Université Paris-Saclay at Orsay, and today is July 15th, 2023. By an extraordinary coincidence, this is both the 10th anniversary of the first commit to Lean by Leonardo De Moura, of course. So GitHub says July 16th, but in Leo's local time it was July 15th, 2013. And it's also the day where Mathlib is fully ported to Lean 4, just by coincidence. And it's also the day where we announced that Mathlib 3 would be no longer accepting new contributions. All on the same day today. The port has been a huge work by many people. Mario Carnero, Gabriel Ebner, Daniel Selsam worked on tools specifically dedicated to translating Lean 3 code to Lean 4 code, with support from Leo De Moura and Sebastian Ulrich, of course. And then the bulk of the actual porting work really started around Christmas, say 2022, 6 months ago, led by Scott Morrison. It involved amazing work, amazing porting heroes. Some of them are well-known, very experienced contributors such as Scott Morrison or Yuri Kudryashov, and you can see Chris Hughes and Johan Komlin and Eric Wieser are there too, but also some people like Ruben van Velde, who was a contributor to Lean 3, but not as much as to the porting effort. And amazingly, we've been also joined by people who I think barely use Lean 4 at all, such as Jeremy Tan and Jason Ewan, who joined us for this porting effort. And of course, many other people contributed. There are 100 contributors to the Mathlib 4 GitHub repository. So the details of this tale will be sung elsewhere. The purpose of this video is not to tell this story of the port, it is to remind you why we've been doing all that. Why this port? Maybe you've been working on the port and you suffered because many little things are understood a bit differently by Lean 4, and so things that seemed simple in Lean 3 maybe looked more complicated and confusing just because they infer implicit information a bit differently. Or maybe you wanted to contribute exciting new mathematics to Mathlib in Lean 3 and you've been frustrated because the maintainer team was focused on the port and not available to help you or to review your work. Or maybe you love Lean 3 so much that you can't see why we need a new version of Lean. Then this video is for you. I will give you a biased tour, quick tour of what I know about improvements from Lean 3 to Lean 4 that I think you will love if you want to formalize mathematics in Lean 4. Note that formalized mathematics is not the only goal of Lean 4. Lean 4 is a great programming language and it should become a great platform for software verification as well. But this is not the topic of this video. You can watch Leo De Moura's fantastic video from iSerm last summer for a maybe more balanced account of Lean 4. And you should really watch it, even if you already saw it. I watched it again last week and I was just as excited as 1 year ago when I attended this talk in Brown, in Providence. So I will not be comparing Lean 4 to other proof assistants such as Coq or Isabelle. This is simply not the topic of this video. So just don't assume that things I will show exist in no other proof assistant. This is not at all what I'm claiming. This is all about comparing Lean 4 to Lean 3. And also remember that I still love Lean 3. We've been doing great things with Lean 3 and I will always love it, but the future is Lean 4. So let's start with a very superficial look at a Lean 4 file. So you can see the first thing that is striking is the code looks cleaner. And maybe it takes a bit of time to understand why it looks cleaner. So maybe the most visible change is the absence of curly braces and commas So this is all space-sensitive code, so the indentation structure the code, just like in Python. Maybe you can see also more syntax highlighting of tactics. And this time it's not because there is a fixed list of tactics that gets highlighted like in Lean 3. The Lean 4 server actually sends information to VS Code telling this is a tactic, you should highlight it. So this is why you have more colors. A tiny thing that is also makes things cleaner is implicit arguments, auto-implicit argument. Notice the variable line here does not say alpha type star topological space alpha. It starts with topological space alpha, and Lean introduces the assumption that alpha is a type living in any universe, just without being told to do so. Also notice the open filter topology set. There is no longer an open local. Open local was a great addition to Lean 3 by Floris van Dorn, who was working on limitations of scope in Lean 3. Now everything is scoped. You can scope everything, and open does everything. Opening the namespace for name resolution, opening notations, maybe attributes, and everything is done in this command. Also note that so there are two lemmas in this file, and one of them is about a function whose range has a least upper bound, which is the limit, because the function is monotone, and the other one, and the function goes at plus infinity to a, and the other one is a dual statement, where the function, you take a limit at minus infinity, this is at bot here, and you get a greatest lower bound. And in Lean 3, deducing the dual version from the main version would look like this. This is the Lean 3 Morse code, underscore, underscore, underscore. How many of them are there? Like 7 underscore. And in Lean 4, you can just use named arguments, implicit argument, to tell that the alpha from the previous lemma is the order dual of alpha that we are looking now. What else? We have the breadcrumb telling us we are in the demo namespace. So and if I go outside of the demo namespace, this demo disappears. So it's useful to know where you are, but actually it's less useful than you think because of another nice feature of Lean 4. If you put your mouse over the declaration here, you get the full name of the declaration as a tooltip. So it's very convenient to know what you're actually defining. And speaking of references and better language server support, one thing that you really like is if I click on tens2, which is our notion of limit, you want to know how useful is that. You can find all references. And indeed, this is a useful notion appearing in almost 300 files, 3,000 times. So you can just see immediately when you want to refactor something, where it's used, what will break. Something else we can already see here. What about now editing the file? Look, this is dot autocompletion. So I start typing something and I got autocompletion of my dot notation. And this is really life-changing too. It's a little detail, but it's very, very useful. And something we can also see about editing file is what if I have a variable that is actually useless, such as a second point in alpha because I copy-pasted something. You immediately get information from the unused variable linter telling you variable a prime is unused. This is also very nice and allows to catch many stupid copy-paste mistakes. So this is what you see from a rather superficial look at a Lean 4 file. It's already nice, but maybe not worth translating 1 million lines of Mathlib code to a new proof assistant. So let's continue and see what about speed improvement. So let's see in a Lean3 file, I'm looking for two lemmas, one lemma. So I'm importing here a lot of the library. So I'm importing stuff in differential geometry and something in algebraic geometry. So that Lean currently has in mind a lot of Mathlib. And I'm looking for a lemma that is towards the beginning of the library, the fact that identity goes to infinity at plus infinity from real to real, and using library search. And you can see that if I just edit this file, I've got the orange bar here telling me that library search is working, and then another lemma that is further away in the library, and I had to wait to get my answer. And every time I move a character, I need to wait for both my lemmas to be found. And now let's compare with the Lean4 version. I hope it wasn't too fast and you managed to see the orange bar. Let's do it again. It's almost instantaneous. And notice we had to shorten the name of library search because typing library search became the bottleneck. That was the thing that took too much time. And the reason why library search works like this is because it does a better indexing of lemmas that is much more behaved when the library grows. And this is super important. More than the current speed improvement, the important improvement is that speed should stay constant roughly as the library grows. And the same kind of improvement is used in the simplifier, and so that also calling simp deep in the library should not be much more expensive than calling simp at the very beginning with nothing imported. So maybe this is not fast enough and you still fear that editing files will be painful. Let's take a Lean3 file with a big proof. So this is the proof of the Baire category theorem for complete metric spaces. And when you work on such a complicated proof and you are towards the end of the proof, the problem is that every time you change a comma to a proof, you have to recompile the full proof. And it's not so bad, and I've got a fast computer and this proof is not using heavy automation, but still, every change in the proof recompiles everything. Now in Lean4, this is still true, but you can save the state of the proof using save, and then after doing that, if you modify the proof, you're only recompiling what is after the save. And in the future, this save will be inserted automatically by more tactics. But you already have this concept of a checkpoint in a very complicated proof. You no longer have to do what we always did in Lean3, which was after proving a half like this, just put a sorry in front so that the proof is no longer recompiled and then move to the next step of the proof. So the speed improvements in Lean4 also allows to build new tactics that would have been impossible in Lean3. So for instance, let's take a very quick look at a test from the ongoing development of Duper. So Duper is a superposition prover by Alex Benkamp, Josh Kloon, and Yisheng Qian, and they are working on it currently. But let's see already what is in this file. So this file has an axiomatization of real and a distance and an order relation and real number, because it's not importing Mathlib or anything. A definition of continuity and uniform continuity, and a proof that uniformly continuous functions are continuous. And this proof just unfolds the definition, and then the goal is just lots of quantifiers, and the superposition prover just does it instantly. I think instantly, more precisely, is in 200 milliseconds. And if you compare to automation in Lean3, you can do exactly the same thing, call Toto and it fails. You can call finish and it fails. And you can call, I don't know, simp and it fails. And it's just not available in Lean3. And we have also the Aesop tactic by Yanis Lindberg, which replaces already tidy and the continuity tactic and is platform both for general purpose automation and for building specific domain specific automation. And really this is only the beginning. So some things change pretty deeply in the Lean core. The foundation is almost the same, but there are some differences. So one thing you will notice is some more definitional equality. For instance, for this in a product, P is in alpha times beta, and P is definitionally equal to the pair made of P.1 and P.2. So when you apply a constructor to a structure, to the structure projections, more generally, you get a definitional equality, and this was simply not true in Lean 3, and it was sometimes a bit annoying. And then the type class system was completely redone, and that would be way too technical for this video, but we can see already one thing that is easy to explain is that the loops are no longer forbidden in the type class search. So let's see maybe the Lean 3 version first. So I'm adding as an instance a declaration which is not an instance in Mathlib, telling that if a type is finite, then it's a fin type. So the difference between finite and fin type has to be is about being data carrying or not, but that's not very important. The thing is that now there is also an instance in the other direction. So when everything is okay, because you assume alpha is finite, you want to get fin type alpha, infer instance will do it, and it will also do it in the other direction. But of course, if you have no assumption on alpha and just want a finite alpha, then the instance search loops and maximum class instance resolution depth is reached and everything fails. So of course, in this example, there is no way it could succeed. But in the next example, I've got, so I define some inductive foo, it has no content, but just add as an axiom that foo, arrow foo is finite, and I want to get the fin type pi instance for the function type, and here the type class search loops, and if you trace the type class search here, you can see so first you can see the very hard to read trace message, and if you are very careful and have good eyes, you will see it looping. You can already notice that my cursor on the right is moving very slowly, so I'm going down very slowly in this trace. It's thousands of lines long. So let's go on the Lean 4 side and doing the same thing in Lean 4, and now the example works, and this just everything works, and if you trace the instance search, now you get those nice structured messages. You can click and see what the trace instance is doing, and collapsing and expanding. I don't want the tooltips. I want to collapse and expand traces, and every trace is like this. And by the way, error messages, let's do that. Error messages in Lean 3 were not interactive, so unknown, maybe that one, yeah, there is not much to interact with, but let's see, if you have this is completely, this is just a string. There is nothing to click, nothing to explore here. If you do this in if you have an error message in Lean 4, it is also interactive. You can also jump to definition in an error message, or everything just works. Otherwise, just undo this error and come back to my example. Something that is also allowed by new type class tricks is heterogeneous operators in such as addition. So let's see how it works here in Lean 3. So I've got a natural number x and an integer I, and I can check I plus, I will stop tracing instances. I can check that I plus x is an integer because Lin inserted the coercion, except that there is nothing interactive, so I cannot show you, but Lin inserted this is a coercion from natural number to integers. But then if you do x plus I, then Lin is confused. It complains that I is an integer, but was expected to be a natural number. So this example is taken from Leo's talk last summer, and in Lean 4 it just works in both directions. And so it would be a bit too complicated to explain why, but there is no longer a problem, and I can see in the message that this is a dynamic message. I got my tooltips. Okay. What else? Oh, big thing. In Lean 4, syntax is a first-class citizen. So that may look very mysterious. I promised I would be talking only about stuff relevant to formalized mathematics, and now it looks like I'm talking about implementation or computer science, but this is really crucial. So when you start with a Lean file, at the beginning a Lean file is a character string, and then Lean has to make Lean objects and expression out of it and do its magic. But in Lean 4 there is an intermediate kind of object which is a concrete syntax tree that has been parsed already. It's no longer a string, but it's not yet really a Lean object, or neither in the theory nor in the meta theory, and it changes everything because now you've got access to this syntax object, and you can go in many directions from the syntax objects. So very quickly, because this is a huge topic, you can play a lot more with syntax to syntax transformation. So macros are transformation from syntax to syntax. So for instance, let's say you are tired of using field simp and then ring, because this is a very common combination. Then I can build my own macro. So it's macro a bit in the sense of LaTeX macros, but a lot more powerful, and including a full typing system, because this is Lean. I mean, everything is very strongly typed. And here I'm saying that when I type field, and with any of the options that field simp is accepting, then I should do field simp with the same option, just pass to field simp, and then try ring. And I can rewrite my proof using field instead of field simp ring. This is a bit of a silly example, but it's showing a macro that does something with arguments too, and not just expanding one tactic to 4 tactics without taking any argument. You can go also from syntax to Lean expression, and this is elaboration, and because now you have access to this intermediate level of syntax, you can write your own elaborators. And you can tell Lean how to go from syntax. You can define your syntax, and you can tell Lean how to go from syntax to expression. So let's take a look, for instance, at Kyle Miller's product notation. So it starts easy. Just look at the set 0, 1, 2, and 3, 4, 5, and take the product, and you get a set here in natural number times natural number. So this is the product. What is this? I'm a bit confused. Oh yeah, sorry, I'm tired. It's getting late. Yes, you get a set in nat times nat. And now I'll do something trickier. I've got a fin set of natural number, and I take the product with 0, 1, 2. And this time, Lean understands that this is a fin set in n times n. And because it's now interpreted this set notation as a fin set notation. And you can even have coercion inserted for you. Like for instance, I've got a filter on a natural number and an ultra filter. And if you don't know about ultra filters, it's not a problem. The important thing is there is a coercion from ultra filter to filter. And this product notation uses the filter product and inserts the coercion ultrafilter to filter. And the magic doing that is a custom elaborator, and we can look at it if you want. This is a non-trivial piece of code, and it will tell Lean what to do when it sees all this file is about what to do when you see this notation times exponent s. Speaking of nice macros by Kyle, there is also the variable question mark that you have in Mathlib 4. Now you can write variable question mark module rm. So first there is no variable r or variable m. This is thanks to the auto-implicit functionality. But you get a suggestion of explaining this to submiring r at monoid m and module rm. So you can leave it like this in your file if you want, or just pretend that you knew all along what was the way to define an r module, what is a parameter to module and what is extended. And we saw ordered close topology in the very first file, and the same, we could have just written this and get our topological space with a preorder and this mixing order close topology. So nice syntax is a way to build Lean expressions from nice looking strings and then syntax object, but Lean also needs to go in the other direction, and this is what delaboration is about. So let's look at this example also by Kyle. So intermediate field, so we've got a field f and a field e, and E is an F algebra, so E is an extension of the field F. I've got an element alpha in E and a set of elements in E, and I can do both adjoining S or adjoining the singleton alpha. This is clearly using the same function, taking F and a set in E. But if you look at how Lean display that, you will see it's displayed as F of S, just as you would write on paper. And on paper, if you lecture about this, you will write once f of singleton alpha, and then tell students that nobody writes singleton alpha, people write f of alpha, and you can still do it. So we could have written this in our file, but what I want to point out here is that Lean is also able to display it in this way, and because of the delaborator doing that. Widgets. We had widgets already in Lean 3. Maybe we can take a look. The tactic state, you can see in Lean 3 the word widget here. It refers to what Ed Ayers did in 2020 to go from the plain text tactic state, which was really just a string, and the highlighting, the coloring is just completely regex based. I did that a very long time ago, in probably 2018 or even, yeah, and that was completely dead, no interaction at all, and then Ed wrote widgets, and it became interactive, and you can click and stuff. But now it goes a lot further in Lean 4. So Ed got reinforcement from Wojtek Nawrocki and Gabriel Ebner, and they wrote a really nice framework for widget and interaction. So let's see two examples. So in this proof, there is a conv in the middle that requires a pretty tricky pattern to zoom on what you want to modify. And so Robin Dunn in Germany wrote a conv widget. I will show you a variant of it, which is the conv question mark tactic, and you can just shift click to select a sub expression. So let's do that, and I just shift click, and the widget tells me what is the conv command you want to use, and then you can do your rewrite. I removed too much of the rewrite, so let me go back. Yeah, I didn't want to lose that rewrite, So I wanted to do only the conf question mark and click this and tell me what to do to enter this pattern and then do my count here. Let's do a more recent one. Maybe we've got this lemma saying that if you got a function from real number to real number that goes to infinity at plus infinity, and you multiply it by a positive constant, then it still goes to infinity at infinity. So this is a slightly simplified version. I mean, this is a specialized version of a proof in Mathlib. And after some manipulation, you have a computation to do. So let's do a computation. So type calc dot. I've got a quick fix suggesting to generate a calc block. Let's do that. And now my calc is started, and I can select stuff I want to change. So just shift click this, create a new step, and in this new step I will write 1 times max b0, and this will be by simp. And then I want a new step, and this time I will change the 1. So click 1, create a new step, and I've got something to type here on the left hand side. That is my question mark, and this time I will write r times n, and this is by G. Conger, which is a new tactic by Mario Carnero and Heather Macbeth that will just prove this for me. This is a new lean4 tactic. And what do I want to do? I want to select everything here because I want to do a Massot, and Massot, this will be an equality, and I will call the Massot, and this is the opportunity to show you the dot dot notation. So in Lean3 you would have said Massot underscore underscore underscore, but in Lean4 the way you say put as many underscore as needed is dot dot. And now what else? And then this is G. Conger again. And that's all. This is my computation done in Lean4. And this is the kind of thing you can easily do with widgets. You can also do more graphical stuff if you work more. And there is this example on the proof widgets library with a Rubik's Cube or graph being displayed or commutative diagrams. But here I've been showing you only the things that are easy to code for you. What else did we have in Lean3? We have the natural number game, maybe. So you know the natural number game. This is a great introduction to interactive theorem proving. Many of you started with that. And you have to read a lot. Because Kevin wrote a lot of explanation, mostly about not forgetting commas that are no longer necessary in Lean4, but also because he could not explain things in reaction to what you did in the tactic state. It has to explain what will happen, and it has to explain that probably after typing something you read what is below the lemma, and you have more explanations about what to do next, but it's not clear when you need to read that. Maybe you try to solve the whole level before noticing there are more explanation below. And how was this created? This was created using, so this is the source code of the natural number game, and it used some infrastructure that I built for my format lean tool. You see there are commands in the lean code with special commands that are parsed by a Python script, and then Mohamed Pedramfar built this web interface, and Kevin Buzzard wrote the levels, and all the explanations are here in the lean file, and the level is at the bottom here, and with more explanation that you've seen on the web page. Now, what does it look like? And this is everything is comment in this file except for this lemma. So from the point of view of lean, almost all the file is dead. I mean, you can see markdown syntax highlighting that is done by VS Code, but it's not seen by lean at all, the content of those comments. and there is only one piece of Lean code, and this is this lemma. Now let's compare to the Lean 4 version. So maybe first the source code. The source code, you can see, has instruction for world, level, title, that are all the metadata is actually Lean instructions. The introduction is also a Lean keyword, so this is highlighted by the semantic syntax highlighting I was mentioning before. So because Lean understands this and it knows it's a command, this is highlighted. And then there are explanations, and then you can see the statement has hint inside the statement. So this framework was built by Jon Oyster and Alex Benkamp in Düsseldorf after initial work by me last summer. And now you can put the hint inside of the proof in the source code, and they will be displayed when people reach that point in the game. So let's have a look. So you've got explanation about addition world, then the game start, and you've got all your tactics and definition and lemmas, and you can see, I was in the middle of the proof because I experimented earlier, but this is a good place to. So I'm in the middle of the proof. I've started the induction and I've done the first case, and now you can see that now I've got the message. Now you jump to the second goal. So let's go back maybe to see that unfolding. So it tells me I can do induction. So you can start your proof by typing this. So I will copy paste this and then execute that line. And now you have two goals, and once you first prove the first, you will jump, and all the explanation happen when you need them. Even if you're in a dead end of the proof, you can see explanation telling you you're in a dead end. And you don't have to type it line by line. You can also switch on editor mode and just type here in an editor with your explanation below. So induction, maybe switching to editor mode in the middle of a level is a bad idea. But you can use either one. So this is because Lean 4 is a lot more flexible in the way you can interact with it. And it's you don't have to hack the editor integration to build a tool such as the, it's here at the beginning of the proof, such that the natural number game. And you can also interact, you can have machines interactive with Lean. So if you haven't seen already the Sagredo demo by Scott Morrison, you should watch this video on the Lean Prover Community YouTube channel. And this is GPT and Lean talking together, and with Lean telling GPT to try harder and trying to progress towards a proof. And this is also allowed by the fact that Lean 4 is much more flexible in the way it communicates with the outside world. You can even build your own front end to Lean and have it do something completely different with your Lean file. So, for instance, this is the output of the informal Lean project by Kyle Miller and myself, and this is automatically generated from a Lean file, and this is an HTML file where you can click to obtain more details about claim. For instance, one can see it suffices to prove, and if you want more detail about that, we see it by the following argument, and you get a tactic state display in English, and this is all auto-generated from Lean 4 code. And this is just writing a different front end using that Lean. I'll let you access everything it knows about a Lean file and do whatever you want with it. And this is the end of my tour of Lean 4 improvements for formalized mathematics. And maybe you're now picturing yourself using the fast library search or the duper tactic, maybe the calc widget, or playing the new natural number game. And this is great. But it also means maybe you missed the main point. And Lean 4 is not about using nice tactics or widgets. Lean 4 is about allowing you to build the syntax, tactics, or widget of your dreams. You should be picturing yourself inventing your own interactions with Lean 4, or at least suggesting these interactions on Zulip. You can start learning today how to program in Lean 4. You can read Functional Programming in Lean by David Schein Christensen. And then once you've done that, you can read the Lean Meta-Programming book by Arthur Polino, Damiano Testa, Ed Ayers, Evgenia Karunus, Henrik Böving, Yanis Limberg, Siddhartha Gejil, and Siddharth Bhatt, and just learn how to do that. And then on July 15, 2024, you'll watch this video again and laugh at me, thinking that I completely failed to understand the true potential of Lean 4. Thanks for watching.